It's okay.
Yes.
Cool. Cool.
So please go.
All right. Thank you. Thank you, Rujitsa. And thank you both, Rujitsa and Moshe, for letting me give this talk remotely. So in the morning, Moshe spoke about LTLF, and I'm going to, mostly in the context of the synthesis problem, reactive synthesis problem. I'm going to talk about the model checking problem for LTLF formulas. This is based on our ATWA 23 paper, which is joint work with Yong Lee, Lucas Tabajara, Moshe Vardi, and Andrew Wells. So why do we need model checking? Well, the argument is that synthesis begets verification. So here is the problem of LTLF synthesis. You are given an LTLF specification, and you want to find a reactor system that satisfies it under adversarial behaviors of the environment. Now, over the past couple of years, LTLF synthesis has become extremely popular because it is much more scalable. And one of the reasons is that it is much more scalable than LTL synthesis. In fact, last year, the SynthComp competition introduced an LTLF track. But what was interesting is that they only had a realizability track. They did not have a synthesis track. So it was only a true or false answer of whether an LTLF specification could be realized. The reason they didn't have a synthesis track is because there were no model checking algorithms. So if you produced a strategy, then there was no way of testing or verifying whether that strategy was correct. So that is what really propelled us, or was one of the motivations for why we started looking at the model checking problem. Now, you would be fair in assuming that, well, what's the big deal? Model checking LTLF should indeed be very, very similar to model checking LTL. And you would be right in assuming that, partly because that's what folklore tells us. In fact, in folklore, LTLF is often assumed to be the simpler cousin of LTL. And from what we know so far is that in most cases, LTLF is easier, if not at most as hard as LTL itself. Case in point being that if you look at the automata constructions of LTL versus LTLF, LTL are automata over infinite words, whereas LTLF are simply NFAs or DFAs. And I don't need to convince this audience that manipulating NFAs and DFAs is much, much simpler than manipulating automata over infinite words. Similarly, the reactive synthesis problem on LTL and LTLF have the same complexity. In fact, if you zoom into their worst case complexity, then LTLF is actually easier than LTL. But this is where the story ends. Because what we show is that in the case of model checking, LTLF model checking is exponentially harder than LTL model checking. So LTL model checking is known to be p-space complete, whereas LTLF model checking is x-space complete. And in this talk, I will try to show you why LTLF model checking is exponentially harder. Before we take the deep dive, let me quickly tell you what LTLF is. LTLF is linear temporal logic over finite horizon. It describes behaviors over executions of finite but unbounded length. The syntax is identical to LTL. So they are Boolean variables and operators, as well as temporal operators like always, eventually, next, and so on. And the only difference is that this is now interpret over finite executions, not infinite executions. So if you look at this formula, always request implies grant or next grant. Just like in LTL, this means that every request is granted within 2 steps. But the models of it would be finite length sequences. So this finite length sequence would satisfy the specification because every true instance of request is followed by a true instance of grant within the next 2 steps. Whereas this sequence would not satisfy the specification because there is a true instance of request, which is not followed by a true instance of grant within the next 2 steps. So let me remind us what LTL model checking is. The LTL model checking problem simply says, given a model M, does an LTL does a given model M satisfy an LTL specification phi? And what we mean by that is, does every execution of the model satisfy the execution? Which is the same as asking, are all the executions of M contained in all the words of phi? Which is the same as saying M intersection not of phi is empty. And here not of phi are simply the counterexamples of the formula F, phi. And now it's well known that this problem is p-space complete. And one of the key reasons behind why this is p-space complete is because the automata that represents all the counterexamples is single exponential in the size of the formula. So if you have a formula phi, you can get the counterexample automata within a single exponential blowup. So what goes wrong with LTLF? So let's go over this. As earlier, a model M satisfies an LTLF specification if every execution of the model satisfies the formula phi. But now this should raise a little bit of alarm because the length of the executions of the model is infinite, and phi is a formula over finite length executions. So a priori, this does not make sense. It's not type checking. So one way to fix this is to say, all right, we'll say that an infinite execution satisfies a formula over finite length execution if it has a prefix that satisfies that formula, right? And once we do this, it type checks. And the reason we care about this definition is because this is exactly how strategies are constructed in LTLF synthesis. So if you look at the reactive systems that are produced by LTLF synthesis, these systems are non-terminating. And the requirement is that these non-terminating models will produce executions of infinite length. And we only require that there exists a finite prefix that satisfies the formula. So in the context of LTLF synthesis, this is the definition of model checking that we require. So now let's work with this new definition. A model M satisfies an LTLF formula if every execution of the model has a prefix that satisfies the formula. So now we say M should be a subset of all of the words, all words of infinite length, which have a finite length prefix. So if we think of this in terms of the counterexamples, we get the intersection of M with the language, which accepts a word if all of its finite prefixes violate the formula, that should be empty. So here, in the case of LTL, the counterexamples were simply not of phi. In the case of LTLF, the counterexamples are for all prefix should satisfy not of phi. And the fact that there is a universal quantification outside of not of phi should already start giving you hints about a potential exponential blowup. And indeed, that is exactly what happens. So without loss of generality, I will call a counterexample automata, given an LTLF formula. A counterexample automata is one that accepts an infinite word if all of its prefixes satisfy phi. So for all prefix satisfies not of phi. On the previous slide, I had for all prefix satisfies not of phi, but it's the same as saying for all prefix satisfies phi. And now, if you think about it, it's actually not surprising, and this is actually quite easy, that if I give you an LTLF formula, then we can easily show that a deterministic form of the automata should be a double exponential in size of the formula phi. Right? So this is not very difficult. We'll not get into details here. But what is surprising is that even the non-deterministic forms of the automata is double exponential in size of the formula phi. Now, in the case of LTL, the reason LTL is p-space complete or is in p-space is because the non-deterministic forms result in a single exponential blow up in the size of the automata. But in this case, in the case of LTLF, we can prove that non-atomistic forms are double exponential. And in fact, it's because of this we're able to show that LTLF model checking is X-space complete. Now, the crucial idea here is really the reason behind this proof is well captured behind why the non-atomistic forms are double exponential. And in the remaining portion of the talk, I'll get into where you get this double exponential blow up in constructing even non-atomistic forms. So here's the problem. Given an LTLF formula, we want to construct its counterexample automata. And we want to show that there's a double exponential blow up. So if I'm able to give you an LTLF formula, which is extremely short, and show that for this formula, every counterexample automata is extremely large, in particular, double exponentially large, then I would have convinced you that there is an unavoidable double exponential blow up. So let me start by giving you a candidate large automata. So this automata represents a language over infinite words. These words are over the characters 0, 0, 1, 2, 3, all the way up to capital D, and a special delimiter character sharp. The words are such that there is exactly one sharp in the word. So there's a finite prefix before the sharp and an infinite prefix after the sharp, infinite suffix after the sharp. And I require that all the digits appearing after sharp are a subset of the digits which appear before sharp. So here, if you look at this sequence, the digits appearing after sharp are simply 0 and 1, and the digits appearing before sharp are 0, 1, 2. So this word is contained in this language. However, this word is not contained in the language because the number 3 appears after sharp and does not appear before sharp. Now, this could be a standard automata, an undergraduate course assignment to show that all the automata for this language are indeed must have at least 2 to the d number of states. And intuitively, there is 2 to the d because you require to store what all numbers have appeared after sharp in a set. And if there are d numbers, then there would be 2 to the d such sets. And if d is represented in binary, then there would be at least 2 to the n number of states. So far we have that there is a large automata, and this automata is double exponential in this parameter n. Now the question is, can I give you a really short LTLF formula such that the counterexample automata for that formula represents this language, right? So let's try to do that. Now here is one candidate formula. And the formula simply says, for all small d in 0, 1, 2, all the way up to capital D, if small d appears after sharp, then d appears before sharp, right? So it's easy to see that for this formula, the counterexample automata, which is for all prefix satisfies phi, if that holds, then the language would indeed be the language we were seeing just now. However, this language the formula for this language would be rather large. And intuitively, this is because it is a conjunction over all of the small d's, and which means that this formula would be at least linear in capital D. And even if you represent this capital D in binary, then the formula would be at least exponential in n. Now this doesn't work for us because we wanted a double exponential gap between the formula and the automata. Right now, our automata is double exponential in n. This formula is exponential in n. It's not our candidate. We want something which is even smaller. So, okay, we take another example. Now, suppose we say that the formula should be such that the last digit of the word should appear before the delimiter. So here, if I give you this word, then if I can guarantee that for every finite prefix, the last digit, if that appears before the sharp, then the language you would get is indeed the counterexample automata language. And turns out that last can be represented very succinctly in LTLF by simply saying that there is no next beyond this point. And so with this, we can show that there is an LTLF formula which can be represented in quadratic inside in n, where n are the number of digits required to represent the capital D in binary. So here we have a formula which is polynomial in length of n, and the counterexample automata for this language is at least 2 to the 2 to the n. So we found a really short formula for which counterexample automata is very, very large. So to summarize, the key intuition is that in LTLF, there is this extra universal quantification on prefixes. And somehow, when we use last, using for all prefixes on a last behaves very similarly to globally over infinite sequences. And this is the key intuition behind why LTLF model checking over non-terminating systems is exponential space complete and not p-space complete. So in summary, if you look at non-terminating models, which is the kinds of models that are produced using LTLF synthesis, model checking them would require exponential space. And this is X-space complete, so it's also necessary. However, if you had terminating models, then that is p-space complete. And this falls directly from the way one proves LTL model checking over, and the proof is very similar to how one does LTL model checking. So the question this opens up for future work, and this is some food for thought I want to leave you with, is if we were to revise the definition of LTLF synthesis to produce terminating models, would that still be as effective? Would we still be able to get algorithms which are scalable in practice? And here is the challenge behind producing terminating models in LTLF synthesis. Suppose we go back to the simplest example, which is that every request is eventually granted. And suppose the ability to terminate is with the system player, not with the environment. Then one way for the system to always win this game between the system and environment, is to halt the game even before it begins. So in some sense, the system can always ensure, can always guarantee winning a game if it has the ability to terminate by simply not playing. It can make it vacuously true. So the question is, if we want more meaningful terminating models or terminating strategies from LTLF synthesis, how should we redefine the problem? And perhaps the issue that I explained right now arises because reachability games, which are used to solve LTLF synthesis right now, generate the most greedy strategy, as opposed to generating a strategy which would be more meaningful. With that, I conclude my talk, and we can open the floor for questions.
Thank you, Suguman. Let's first thank the speaker. Are there questions?
He's an author of the paper.
But maybe he had some new ideas. I just wanted to ask what happens if what happens if you add past? So LTL with F with past operators. Should still be X space, no?
I wouldn't. Well, if you had past operators, then well, I can't be very sure about it because I haven't really looked at what blowups happen if you have the past operator. But I would believe it would be very similar, because when you have past, it would boil down to whether yes, so if you have past, you would still require just being able to say that for any character that has appeared after the sharp, you should have seen it somewhere in the past. That would still require some sort of a conjunction on the characters. So I think even there, you would have to use this trick of saying that the last character has appeared somewhere before. So I would still think that there should still be an extra blow up than what is standard in LTLF with past or LTL with past. I would still expect that.
Hi, Suguman, Anna here. So you put this in very interesting future work. I suppose you also have some insights or thoughts on what are meaningful strategies and how do we make reachability games generate those?
Yeah. So in this context, so let's look at this example. Every request is eventually granted. A meaningful strategy would be one that engages with the environment, right? So it should be one that says, well, irrespective of how many times the environment plays, I should always be able to, my strategy should be such that anytime I terminate, I should be able to guarantee that the formula is satisfied, right? So the formula doesn't need to be satisfied on all prefixes, but anytime I decide to terminate, it should be satisfiable. Which is different from saying, which is different from what reachability games do, because the way strategies are extracted in reachability games is that all you care about is to reach an accepting state at most once or exactly once. And the moment you reach an accepting state, you never say, can I reach another accepting state? Right? But that is the flavor of strategies that perhaps we want in terminating models. That sure, you may have reached an accepting state at the 0th step, but can you reach another one in the future? And anytime you reach an accepting state, you ask the same thing, can I reach another one in the future? And then you give the system the ability to terminate anytime it visits an accepting state. So it has this flavor of Buki, but it's not exactly a Buki. So those are my initial thoughts.
Thank you. And since there are no more questions and we are at 3, let's thank Suguman once again for her great talk.
Thank you.
Thank you, Suguman. And I think that